So that's the species Hamiltonian. And last time we calculated H1. We conclude that H1 is 1 over 8 pi squared, sum of 1 minus P L plus 1, the L from 1 to the length of the chain, and that's the also known as the Heisenberg x1/2 model. It's well known to be integrable. We're not going to discuss the exact solution of this on the finite chain, which will not serve any purpose for later generalization. We're just going to discuss this in the limit of asymptotically very long chain. The approach we're going to take is to consider this configuration with all the speeds down. Remember, this was the operator trace d to the L. Chiroprimary, that's due to a square graviton. We're gonna let's say if we flip one of the spin that corresponds to inserting replacing one of the d with an x. Now this operator by itself is still going to be a chiroprimary because the momentum x is restricted to be 0. The momentum of the magnon is restricted to be 0 because of the cyclicity of the trace. So you need at least 2 magnons to make this operator non-zero. So I have some over there, and they're going to move with, let's say in this example, equal and opposite momentum. So that corresponds to some, so let's say this is L1, and this is L2, and we're going to have e to the I P1 L1 plus P to L2 summed over L1 L2. And of course, P1 plus P2 is restricted to be 0, and this will be a operator that is going to be expected to be an energy eigenstate or an eigenstate with bidilatation operator to the extent that you're in approximation where this chain is very long and the magnons are far separated. Because when the 2 magnons are close by, you have to be you have to be careful. In fact, let me say it this way. So in fact, at this level, we already had to be careful because this wave function should be viewed as this operator. You can think of this coefficient as a kind of a wave function of 2 particles on the chain. It's an asymptotic wave function, and let's say this is an expression that is valid in the regime when L1 is, let's say, less than L2, and then there's also the regime when L1 L1 is greater than L2. And you have a similar thing. So in fact, let me abbreviate the notation at this stage. Let me use it just to be able to write a formula without having to keep writing this chain of traces. Let me just describe this in terms of the wave function. So I'm going to call it L1, L2, X1, X2 in the usual wave function notation. All right, so I think of this as the wave function corresponds to I P1 X1 plus P2 X2 of the plane wave form. This is where in the regime when let's say we're in a regime when X1 is much less than X2. Now, the wave function has to be the form of a scattering wave function in that asymptotic regime. So you know that there's also going to be a term with e to the I P2 X1 plus P1 X2, whose coefficient is a phase, which is the S matrix element, in this case, just the phase, S P1 P2. Which is the 2 scattering amplitude in the kind of elementary sense of quantum mechanics in 1 degree of freedom. You know, these are by construction identical particles. So of course, psi x2 x1 is the same as psi x1 x2 for in the opposing, so it suffices for me to say what this is in the regime X1 is much less than X2. All right, so far so good. Any question about this? So this is supposed to be the asymptotic, let me emphasize, this is the asymptotic wave function. Wave function of the magnet, of the state of a paramag. Now, to be able to write this, we have already made assumption of integrability. Not quite. We have made a kind of a partial assumption, which is that the scattering is elastic. There's no, you know, the particle number cannot change. Particle, in this particular case, the particle type also cannot change, but more generally, you could allow particle type to change if they have the same dispersion relation. So what are the other shocks that? Oh yeah, okay. All right. Okay. Now, of course, you all know how to figure out what this S is. You just plug into the Schrodinger equation. This is elementary, but let's do this anyway. So, following the equation, let's say H1 of psi equals E of psi, right? And so solve the Schrodinger equation. So this says that the 8 pi squared E psi, while the only non-trivial part of the equation is when x1 and x2 are next to each other. That's the only case when interaction is non-trivial. Like this, x plus 1 is equal to well, into this 2 psi x plus 1 minus psi x minus 1 x plus 1 minus psi x plus 2. So that's a general expectation. But of course, in order to figure out what the S is, you actually have to solve the entire wave function to fix it. That's how you know. This is no different from a scattering particle of potential barrier, right? Hope you all have done that in your undergraduate quantum mechanics class. It's the same logic. Well, you know, I mean, you have to look at the x1, x2 nearby within the range of interaction to be able to read off the S from the Hamiltonian. I mean, of course, when x1 and x2 are separated, let's solve the equation trivial. The energy, of course, is sum of the energy of the two particles, like any scattering state does. So the Schrodinger equation is solved trivially when the particles are far separated beyond the range of interaction. The only non-trivial part of the equation is when within the range of interaction. And now, of course, if you plug this in, you can easily read off the S's, the S from doing some very trivial linear algebra. And the solution is SP1P2 is equal to minus 1 minus 2 e to the I P2 plus the I P1 plus P2 over 1 minus 2 I P1 the I 1 plus P2. And convince yourself that this is actually a phase as required by unitarity. Anyway, that's a scattering phase in the case of this, the simplest kind of magnon in the simplest possible non-trivial model. All right. Now, what is less obvious is the integrability of the which implies the factorization of the 3 to 3 and 4 to 4 magnon and so on and so forth, right? So this is 2 to 2, but there's also 3 to 3 and so on and so forth. So for example, 3 to 3, you have the P1, P2, P3. The idea is that first of all, the particle type and momentum cannot change. Well, in this case, just the particle momentum cannot change. So the three-body S matrix is the product of these two S matrix elements. Why is that true? The argument is standard one. The idea is that you're scattering these wave packets. They're all moving with some momentum. Of course, for the formula of the usual S matrix in the usual scattering theory, you need to assume that you're essentially going to be taking a limit starting from the configuration where the wave packets have some finite but sufficient large width, so the momentum is sufficiently peaked, but they're sufficiently far separated, in the far past or in the far future. Now, we're in 1 + 1 dimension, so generally, depending on how you arrange these wave packets, they may scatter like this, or they may scatter like this, or maybe somewhere in between, like this. Now, of course, you would expect that if you arrange wave packets such that the time separation between this and this and this are far long enough, then you can really think of the S matrix element as a result of the product of these three. But what about this situation? It doesn't look
long enough time that you can view them as asymptotic states in the intermediate, right?
That's correct. That's exactly it, right? But this, of course, is not true in a general quantum field theory, because I mean, if you don't separate far enough, then it's not true in the ordinary quantum field theory. But in the integral theory, the idea is that you have translation generators. You have translation charges that are of the form. So usually, let's say you write some e to the I alpha p as the translation operator by some amount, let's say, call it delta xp. So this will be the translation generator by some amount delta x in space. But now you have some charges like this, f of p. In fact, let's say if you have an ith particle, the charge will be of the form sum of I fpi. So the charge will still be additive with the particle, but it looks like this. And now you can choose this function to be, this function could be peaked over some momentum p star, this f of p, so that if you have these kind of infinite conserved charges, you can choose to move particle with the one specific momentum and not the particle with the other momentum. So you're allowed to take this line and just move it as far as you want, and the symmetry will commute with S matrix. So, okay, so that's the reason for the factorization. So that says that this has to be equal to this, equal to that. Right. So this is the only place where the infinite number symmetry is used, and you see you need the infinite number kind of independent symmetry so that you can cook up any symmetry charge that the charge also had to be local, of course, so that it's sum of the individual particles. But if you assume that there's a symmetry, then you have this factorization property. Now, this, of course, is well known in large class quantum field theories. In the quantum field theory context, it was first pioneered by Zamolodchikov. Like Sine-Gordon model has this OM model in 2 dimensions. It'll have this property. But now, of course, we're not talking about relativity quantum field theory. We're talking about spin chain, but this particular spin chain will also have this property. That's a well-known fact. And this particular property is going to be it's conjectured to extend to all others for the spin chain Hamiltonian of the equals for supermangles. Okay, so anyway, from this you know that anyway, let me write a formula to just draw the picture. So the 3 to 3 matrix factorizing the product of these three, and then so on. So just take all the possible pairs and take the product. That give you the n-body S matrix then. So now let's come to the beta ansatz. So this is the simplest, by far the simplest form of beta ansatz. Things will get much more complicated later. but now we're talking about the situation with one species of the magnon. So we are interested in the spectrum of this thing on the large but close chain now, with possibly multi-magnons. So the condition you really have to impose for the closure of the chain is just that this wave function has to be periodic like this. Here, because these are all bosons, it suffices to write this equation in the regime when x1 is much less than x2, much less than x3, and so on and so forth. But then if I shift x1 by L, under which this is supposed to be periodic, I'm kind of move it all the way to the right. So I maintain that order of the increasing order of the coordinates. Now, if you just literally plug this asymptotic wave function into that geodesic condition, you find a relation that says because this right hand side, this x1 is going to pick up this dependence. It has the e to the I d1 L factor, and then you're going to have well, okay. And first of all, you have to work this out more carefully because you have to write now that the M body wave function, which will involve all the possible permutations, and for every permutation, there's a corresponding S matrix element that's a product of subset of the two-body S matrix elements. Okay, it's a yeah, it's an exercise that requires a little bit of thinking, but at the end of the day, the result is has kind of a very clear interpretation. So product J from 1 to M, let's say, but generally, so PK for any of the momenta, J not equal to K, say, not equal to K, from 1 to M, S PJ PK. This is intuitively very clear. It just says that if you look at the wave function, let's say focusing on the kth particle, keeping all the other particles fixed, you look at the wave function as a function of the coordinate of the kth particle. It has to be periodic. But as you move along the circle, you have a phase due to the plane wave, but then you also have the scattering phase, and they have to cancel. The scattering phase with every one of the other particles. Right? I mean, intuitively, this is kind of obvious if you think about fixing all the other M-1 particles as some kind of defect. You just look at one particle in the presence of the other particles, and every time you cross the defect, you take out a phase, and then you come back. The phase has to be 1, so you have the phases of the e to the IPX together with the scattering phase. You just have to. There's a convention you have to check. You have to make sure that this S and not S inverse. I believe I use a consistent convention here that can easily verify. And that's it. Okay. So you have this for every K from, let's say for every K from 1 to M. So that's a system of of M equations. And of course you have this M momenta pk. So you might expect that you can solve this equation. I mean, what happens is that this equation is going to have a discrete set of solutions. So essentially, it's clear that if the phases are 1, the solution is just a quantization of the momentum. So you have the units of momentum quantum numbers, and the solution to this equation is just going to be generalization of that. So in the absence of phase, you have every particle is in some mode with some quantized momentum, and this momentum will, of course, get shifted once you have a non-trivial scattering. That's going to be what the solution to this equation will look like. You have some, of course, infinite set of solutions, but they're discrete because they was this momentum quantum number. We'll come to the solution to this equation when we actually need it. For now, let me move on. So anyway, I mean, this is how the what's known as the asymptotic beta ansatz would work for this very simple Heisenberg spin chain model. Let me mention that just incidentally, it turns out that this equation also holds at finite m and l. That's not something that follows from, that we have discussed, but I can show that it's actually exact at finite m and l. But as I mentioned, that exactness is not going to generalize for the spin chain of equals force around super so I'm not going to emphasize that. All right, any questions before we move on?
So can we get like the square root from this, or what is the point? Like, are we trying to find the PKs?
We already know the PK. So sorry, no. The square root formula. Okay, maybe let me finish that point. What is the energy of this? The energy of this is the sum of K, E, PK. We know what the answer to that is. That is equal to sum over K. Well, of course, at this order, it's going to be this thing. Let's select some lambda sine squared PK over 2. Right? That's the dispersion relation we saw last time. More generally, there's going to be some square root formula, but the square root is not here because I've expanded to first to 1 order. This is just a 1 loop Hamiltonian. Everything actually because I factored out to this lambda that this by my convention, the lambda is outside. So the square root is not yet visible because I'm only working on 1 loop order.
If I know S and I know PK, like what is this formula good for?
No, what do you mean you know PK? You don't know PK. What do you mean you know PK? The whole point is to figure out quantitative condition on PK.
Oh, okay. I see. Okay. Doesn't the condensation condition follow from the sign being periodic, or?
No. The beta ansatz is a quantitative condition. This is a quantitative condition. There's no other quantitative condition. Let me make this more explicit. Let's take the log of both sides. I pk L is equal to 2 pi nk plus log 2 pi I nk plus log of that. These are the momentum, quantum numbers if you wish. So the nks are supposed to be integers. Well, you have to figure out what integers are admissible.
What specifies?
Huh?
What specifies the NK?
It depends on the form of the scattering phase. Your particle might secretly look like fermions. It could be that as the scattering phase, as 2 momentum collide, the scattering phase approaches -1. So if you have like a fermion, in that case, you cannot have coinciding NKs because the Pauli exclusion will emerge out of this. So it's just the fact of whether you can solve the equation or not. It's merely a fact of whether you can solve this system of coupled equations. Any other questions?
Is there a way to write quantization condition in terms of the old-fashioned quantization?
That's not relevant for what we're discussing. All right. That's it. Anything else? I think that's all I'm going to say about this 1 loop story. So now we're going to go beyond the 1 loop orders. The idea is to explore to the maximum extent the consequence of symmetries. So we're going to start with trace leads to the I think that now I want to just call it J because J is the angular momentum charge, the R charge, as one of the SO6 Cartan generators. So of course you have the PSU 2,2/4 algebra. That algebra is spontaneously broken by the choice of this Magnon vacuum. Think of this as a state with no Magnon. This is the vacuum. So it's broken to a subalgebra, which is SU 2/2 direct sum with SU 2/2. There are two copies. And let me label the generators. I can so each SU2. So each SU2 /2. This one contains a bosonic subalgebra of SU2 direct sum with SU2. Okay, so in total 4 SU2s. They could get a little confusing. I don't have. I'm not gonna label the actual algebra themselves. I'll just write it, this label them with indices. So so the first SU2/2, the generators I will denote by L alpha beta, R A B, Q alpha A, and S alpha A. All the indices will be raised and lowered with epsilon. Hence the epsilon, alpha beta as usual for SU2. All of these are double indices of SU2. So the first SU2, this is the label, the indices are alpha beta. The second, I use capital A and B. And this one will contain some SU2 plus SU2. And I'll use the dotted indices, alpha dot, beta dot, and similarly A dot and B dot. Okay, so that's going to be the convention. So Q and S are the supercharged and special supercharged as usual. R is the R symmetry, and L stands for Lorentz generator. That's where they come from, right? And likewise, so here I have this L. Let's call it L bar alpha with the dot, R bar, Q bar, S bar. Okay, so this is a subalgebra of the full working form algebra that's going to preserve this trace Z to the J. Anyway, so there's some more convention that are stated in the notes. Let's see, what do I want to say? Let me mention that as usual, the QQ, let's see. Right. These generators are chosen such that the QQ commutator equals to 0, so it's SS. The QS is non-trivial, and the QS would involve a alpha beta R A B plus epsilon A B L alpha beta plus 1/2 epsilon alpha beta epsilon A B times H, which is the Hamiltonian, or minus I times the division. Well, I guess I should. Well, technically, I should really include. Well, let's see. Yeah, if I can you think about it, I wonder if I should have adopted a better notation, because I should really say that H is part of the generator. Since I'm talking about SU and not PSU, so there's extra like central. Well, there's extra bosonic generator that commutes with the SU2 and both SU2s, which is this H that shows up here. But it's the same H that's shared by the two. So I think actually this notation is slightly problematic. That's kind of funny because this is certainly the standard notation in the literature, but it is the same H that's shared by the two elements. Said about this. Well, I guess there's no contradiction just because I can say that it's yeah it's really this SC2 plus SC2/2 multiplied by a central element, so that the two H's are identical. That's what algebra is. Okay. Now let's discuss how the algebra actually acts on the fields. So previously we're talking about the SU2 sector, which was replacing the Z by X. Now that is of course this algebra is going to take you outside of the SU2 sector.
How does this algebra acts on the fields?
Yeah, I'm about to say that. Okay, so in our convention, Z was pi 5 plus pi 6. All right, so let's look at the other elementary fields you can possibly replace Z with. So they're pi 1, pi 2, pi 3, pi 4. And then there's some fermions. Let me write them as lambda I alpha and I dot. And we have these fermions, but we're not going to look at all of them. We're going to look at the ones that are that can have a chance in participating in operator mixing. So remember we have discussed kind of related point last time. We're going to restrict. So let's say you have a H1, H2, H3, which are the three Cartan generators of the SO6 R symmetry. Right? And this one has a H3 charge equal to 1. Now we're going to restrict it to the states with delta minus H3. So delta 0, this is the classical dimension. Equals to 0. Oh, this typo. Equal to 1. It meant to write this equal to 0. That was weird. Yeah, so we're going to restrict to the states with this property, and so that the states only mix among themselves under perturbative operator mixing. So I see why I wrote this. Sorry, no, the states with this property will just be the Z themselves. But now let's look at the elementary excitations where delta 0 minus H3 is equal to 1. So more generally, this delta 0 minus H3 is the quantum number that counts the number of magnons. So
Why is the case?
by definition. What do you mean by the case? It's a conserved charge. The Opper mixing doesn't change this. And every time you excite a magna, like replace Z with X, you change this by 1. Right? So for the one magnon state, we'll focus on the operators you get by replacing let's say one of these with one of these other fields. But you want to maintain that property. Okay. So all of these phi 1 through phi 4, they have that property, but they have H3 equals 0 and delta 0 equal to 1. Now the fermions, they have what are these? So they have delta 0 equals 3/2, obviously, and H3 is going to be equal to plus minus 1/2. So here you have 8 fermions. Here you have 8 complex fermions. So in total 16 fermions. Right? This I run from 1 to 4 and alpha runs from 1 to 2, and this related by conjugation. Now we're going to be interested only with the ones with H3 equals plus 1/2. So that picks out half of these. And these can be labeled. Let me see. They can be labeled. They'll turn out to transform. Okay, so let me give let me now also say how they transform under these symmetries. So these things, these phi's, I'm going to label them as phi AB. AB dot. You can easily verify that this is because of SO4, SU2 plus SU2. And so it has a SU2 index and another SU2 index from this SU2 and that SU2. Okay, that hopefully is clear. Now the fermions, we need to have 8 fermions that satisfy this condition that delta 0 minus H3 equals 1. And they will transform in the A beta dot and alpha B dot. What else can it be? It's kind of obvious. It has to be the transform. All right. And there's one more thing you can do. You want to use the gauge field as well. But the gauge field, of course, A mu cannot enter by itself. It has to appear in the form of derivative. I got D mu. The D mu, of course, the alpha beta dot. So here you want to think of the insertion of D mu as also a magnet. And you also have this property delta 0 minus H3 equal to 1. All right, so far so good. Any questions?
I'm a bit not clear about this like classical dimension.
Yes.
Just like, is it that like an element that appears in our algebra, or is it like somehow?
No. Well, what I'm saying is that no, it's not an element that appears in algebra. But I'm saying that this algebra is such that I mean, this is a shortcut to keep track of what things are related by the algebra. Nothing more than that.
But then, like, I'm a bit worried about because there's no algebra that.
There's no operator mixing between things of different classical dimension. First of all, we're doing perturbation theory. We're doing planar perturbation theory. This is just a shorthand to figure out how the Q acts on all the fields. Yeah, if you want, you can just go look at the actual transformation and work it out. I'm just giving you a shortcut. Nothing more than that. But of course, the underlying assumption is that you also have the S by some of these. They close into this algebra.
So there was H3, it was plus minus half. We just took the half part, so the lambda bar goes away, or is the other new fermions combination of lambda and lambda bar, because one has dotted index beta, so that's the lambda bar, or how do we?
No. Each one is let's see. Yeah, sorry. You're right. This alpha is the same as this beta dot index. So this can give you this, you that. That's correct.
But
Yeah,
we
yeah,
don't
yeah.
bar one of them.
Huh?
We don't put the bar on like.
It's just my notation.
Yeah.
I think I don't put the bar, but that's just no. Actually, I think in the notes I did put the bar. I think I put the bar, right. So I guess I would bar on this. Oh, the notes I actually put the bar on the other one. Well, that's okay, but that's just minor notation because for the reason that will become okay. Let me write this right here. It's going to be convenient to use a tensor product notation. I'm going to write this as phi a tensor with phi bar b dot this var phi. Okay. At this point, this is just notation. That doesn't mean much. But you know, because of the structure of the two SU2/2 algebras, it's going to be useful to just for simplicity of understanding the symmetry constraints, it'll be useful to think about this left and right sector separately, and then you can put it together at the end. So this is what that notation is for. So in the same way, this lambda can be represented as phi a tensor with psi bar beta dot, and this can be represented as psi alpha tensor with phi bar b dot, and this will be represented as psi alpha tensor with psi bar beta dot. Let me put a z here. So this thing, of course, has to act on some z, and so now the the supersymmetry transformation is going to take phi to the fermion lambda, but the lambda, if you add on lambda again, it's well, okay, we'll see what we get. There's a bit of in principle, there's a bit of algebra you have to check to see that the actual supersymmetry transformation kind of boils down to this very simple action of to come to symmetry, but you have to make sure that all the commutators work out. So, for example, okay, so how does supersymmetry act? The claim that the supercharges act in the following way. I'm talking about now that these supercharges of this SU2/2 algebra. So this acting on so the first claim is that these set of charges, their action on these magnons will just factorize into the independently on the left and the right tensor factors. Okay, so with that understanding, I'm just going to write how this acts on this bar phi. This is going to give you epsilon AB psi alpha. What else can it be? UA alpha A. Now psi beta will have to be proportional to epsilon alpha beta phi A. I'm there with Z. It has to be a commutator. Well, it's either going to involve this commutator or involve the, I guess, the field strength. But in order to be able to match the SU2 indices, that's the only thing that can appear. Likewise, the Q bar will act on the anti-holomorphic sector. Well, you see that now there's something a bit non-trivial that you have to actually verify, right? So this D will actually appear. So for example, if you take phi, tensor with phi, I'm not going to bother with indices, right? So the idea is that if you act on this with Q, you're going to get psi tensor with phi bar. But if you act on this with Q bar, you're gonna get with psi and psi. And in the actual notation of the fields of the supernomial theory, this is this scalar field phi, this is the lambda, and this is d mu z. You have to check that this actually works out. But the claim currently it does. The story would be nonsense. Okay, so this is how you know that the SC2 algebra actually holds. It's not totally trivial. Let me say that this is a funny notation because he asked what this means. So this notation means that if I take this tensor with something, it's defined to be the same as phi a tensor with that thing connected with z, right? So otherwise it doesn't actually make sense. But you know, with this understanding, this operation makes sense. Anyway, you have to first of all check that this actually works, but this of course we checked it in the early days.
Can you explain again, like why, like only the operator with the same quantum number, like delta 0 minus h3 can only mix?
Because that quantum number is preserved by the SC2/2 algebra.
Oh, so H3 is preserved and delta 0 is preserved.
No. What do you mean? The H3 and delta 0 are separately not preserved. It's the difference that is preserved, right?
But delta 0 is it's not an element of the algebra. How can it be preserved by like the?
No. What are you talking about? I'm just saying that Q has H3 equals 1/2 and delta 0 equals 1/2.
Oh, I see.
So that's trivially true. Right? Any other questions? All right. Now, let's examine. Okay, so the idea is going to be that the magnons form a sort of elementary magnons. At the beginning, we knew x is just one of these phi's. Right. In fact, let me see. I think I can. Yeah, I think I can identify x with the phi 1 dot. In fact, I can choose x to be any phi. I can replace x with any phi a b dot if I fix that index convention. In fact, in terms of, let me say this terminology. So, you know, this is what we call the SU2 sector, right? You could have considered instead B1 dot. This one is not the same as that one. That one is the index for this one of the SU2. This one is the index for another SU2, right? This is the alpha beta dot index. That is the AB index. Hopefully you know what I mean. All right, so I can take this. Let's call this D. Some literature often we call this D plus. It's one of the derivatives combination. It's a complex combination of the. It's a derivative in the direction of a null vector. Let's play this. So, you know, at the beginning, instead of talking about replacing z with phi, I could also insert these D pluses. This is known as the SL2 sector. Well, I guess I guess depends on the yeah, I guess it depends on signature. I mean, this ST2 could be replaced with SL2. That's the reason. But let me not worry about that distinction. Yeah, but maybe I should really write this as SL2. Anyway, if you don't worry about the random condition of the generators, of course, this algebra is nice. That's what I want to say. Okay, so in terms of physical interpretation, of course, mentioned last time that this SE2 sector magnon, this in the semi-classical regime from the bulk point of view corresponds to this giant magnon that's kind of this string that's extending on the sphere and is spinning around. This will SL2 sector excitation correspond to expanding the string in the ADS direction. Right? So, for example, this Fuzzy spinning string is going to be a state with a lot of D plus excitations. In fact, it's going to be a state with a very large number of D plus excitations, larger compared to the length of the speed chain itself. I mean, in terms of the number of Cs. Okay. Now, okay, the idea is that these elementary magnons, which are these phi's and psi's, they're going to be organized into representation of this algebra. Let's study that representation. So this representation in some sense is like the fundamental representation. It's like 2/2, you have two bosons and two fermions. But we need to keep track of this commutator with z's. Right? In fact, you would imagine that you can already see this, that you don't, if you want to talk about the magnon state transform algebra, you do not want to work in a position basis because this commutator is going to move this phi up and down the chain. And you should pass to the momentum basis so that this commutator gets diagonalized in the momentum basis. So let's do that. Let's consider, so this capital phi represents any one of these magnon excitations, P for momentum. And for now, I'm going to consider the infinite open chain. Just don't worry about setting the total momentum to 0. So we're for the infinite chain, let's forget about the cyclicity of the trace. And let's consider this plane wave state, magnon, phi z, and this is the out entry that I replaced with the phi. Okay, so then you know that if I apply this kind of algebra, if I encounter something like this, which we will encounter P. So let me just replace the phi with phi z commutator. That of course is equal to, well, write this out, PL z phi z, where this is L. You insert another z that gets buried in the right side of the chain. Sometimes you have to keep track of the length, but that's easy to keep track of. And the sum of e to the IPL to the top, this will be minus commutator, z phi All right, so now this is L plus one. Okay, so now you can, of course, group these two terms together. This is equal to 1 minus e to the minus IP by p, notation, standard notation, in this context, z plus. Z plus just means that I keep track of the fact that I'm inserting extra z on the right-hand side. Okay. So if you actually check according to this rule, then according to these transformation rules, it's very simple, but has non-trivial consequences. So you just check how the Q's acting on these magnons on the open chain. You'll realize that I said earlier that Q commutator is 0, but once you allow yourself to consider open chain, Q commutator is no longer 0. So you can just really check the algebra. You'll find the following. You'll find that Q alpha A, Q beta B, is equal to epsilon alpha beta, epsilon AB, times the central charge term. I'll call it curly K plus. In Biser's paper, I use this horrible math frac notation. I can never tell which letter it is. It's curly K. Well, it's easy to see. Like for example, you take this commutator acting on the phi twice, you're going to get phi commutator with z. So this curly K plus is basically this operation. The curly K plus, so what is curly K plus? The curly K plus, I'm going to say that write it in the following way. So acting on a single magnon, it would be some function K of P, Z plus. That's what I see from here. And this function of momentum, we also have calculated optimization. So keep track of normalization here. So this is going to be equal to some number h times 1 minus e to the minus e. Right. Now, what is h? Now, you might say that I can use you might say that you can just look at how the fields transform under the classical supersymmetry variation. It's going to be some generally could be proportional to the Tuff coupling lambda. Or could involve Tuff coupling lambda in principle. But we're going to work in a normalization convention where Q and S are going to be complex conjugates of one another. Well, they're going to be Hermitian conjugates of one another. This is in the upper language, you'll be in this about the radial quantization. So think of this as just a super theory on the sphere. In such a convention, the normalization of the Q is tied to the, so the normalization of Q will be unambiguous because the QS commutator have to involve the this proportional dilatation operator, or involves the dilatation operator. And so once I fix the normalization convention of the algebra generators, there's implicitly a normalization of Q that is chosen that is tied to a normalization of S. And that will generally get renormalized in perturbation theory. So you don't necessarily know what this coefficient is. But let's just assume that's a function of lambda, the total. In a similar way, you'll find that S alpha A, S beta B is going to be equal to epsilon alpha beta, epsilon AB, curly K minus, curly K minus will be equal to KP, the same function, comes conjugate, it's minus IP, there's a plus IP there, here, and the Z minus. The Z minus is the operation similar to Z plus, where the Z minus operation removes a Z on the right-hand side of the chain. The right-hand side to the magna along the chain. And this is kind of forced on you by, if you demand the S to be the Hermitian conjugate of Q. Okay. Now there's one important comment I have to make, which is that now, of course, this action has to also extend to the multi-magnum states. We're going to, for now, just assume that the magnums are kind of sparse, so they can always be sort of separated from one another. But nonetheless, if you look at how this thing acting on the multi-magnum state, what is 3K plus acting on 5P1, 5P2? I'm assuming that when I read this, this is like in the sense of the scattering wave function. That I'm assuming that I'm working in the asymptotic regime where this 5P1 is reached by a wave packet. That's this first one to the left of the right of the second. So this well. Sort of by definition, it's going to be something that, well, by construction, it's going to be, it's going to act on this by replacing the first phi of normalization with the phi z commutator, plus the second term, which is the second phi with the phi z commutator. And so that's supposed to give us kp1 phi p1 z plus phi p2 plus kp2 phi p1 phi p2 z plus. Now you have to remember that these two are not the same, right? So the k is not additive. Well, but you can easily make them the same. Move this z plus to the right. If you include a factor e to the minus I p2, then that they're equal. Okay. So the same thing is the same as kp1 times e to the minus I p2 plus kp2. And it's a little exercise you can easily do in 10 seconds. You see that this is equal to k of p1 plus p2. Right. So k is not additive, but p is additive. And so this formula actually holds for any number of magnums, where the p is interpreted as the total momentum of the magnet. So in some sense, this is a bit like you can think of this as kind of like a deformed version of some kind of supersymmetry algebra. Usually you say QQ anticommutator is equal to P. Well, here the QQ commutator is equal to 1 minus e to the minus IP, which is kind of like P. Now, of course, we don't see this on the closed chain. On the closed chain, P is always 0. So this central extension is only visible if you consider the open chain. But that's going to be the key. Now, given this algebra, of course, there's also the QS commutator, which is unmodified, that involves the, the age and the things, L and R. So once again, you have a BPS bound, but now you have a BPS bound that bounds the energy of H in terms of the this SU2 quantum numbers of the multi-magnum states. And let's focus for now on the single magnum. The single magnum will be special because the single magnum, as we said, is in this 2/2 tensor 2/2 back to left and right. You just use this notation. This rather two left and right SU2/2 algebras. So forget about, let's focus on the one side. This will be what is known as a short representation. And of course, I'm talking about more specifically about the magnum state with a definite momentum. So magnum state with definite momentum is going to be in a shortened representation, and that will saturate the BPS band. And that's why it's possible to determine the exact expression relation for a single magnum. It's because it's saturated BPS band. But the BPS bound here takes a unfamiliar form because the supersymmetry algebra is deformed in this very nonlinear fashion. So let's see what that actually is. So now let me rewrite this in terms of the more exact formula of the one magnum state with definite momentum. So I would write by P. This is, let's say, we call this alpha P. And this coefficient, we don't know what the coefficient is, A for I. Let's call this I A of P. A is some function of the momentum P. Right? Here, let me call this one IBP, B of P. To be careful, I could put in Z plus here. Right. Commutator. S is going to act similarly. S by B of P. Let me give you I C of P, epsilon A B, psi alpha B Z minus. And finally, S of A psi B. I D P epsilon alpha beta by A. Right. Now the ABCDs, of course, are not arbitrary. We already know. If you already know this form of the algebra, so we know that the A and ABCD are tied to one another. You find that AB equals K, CD equals K star. But if you look at this QS and commutator relation, you will find that further relations. Now we essentially pin down this BPS bound. So AD, you'll find AD minus BC equal to 1, and AD plus BC was H. I will not check. I will not be checking this on the board. But this is just all from literally taking this and act on these on the states into this proof. Right. Okay. So now we can use the familiar formula from your high school, right? So let's say the squared minus AD minus BC squared equals 4. Get 4 ABCD. Right. So this means that H squared minus 1 equals 4 KK star. And there you have it, the BPS bound. So H is equal to square root of 1 plus 4 KK star. That's where the square root comes from. You see, this K must very get sign square root of P over 2. So let me just complete that formula is equal to 1 plus 16h squared times sine squared e over t. So this is a key result in the early days of integrability. We're not really using anywhere close to the full power integrability yet, but this is already a very non-trivial result. This result very naturally passes two crucial checks. I think I mentioned this at the end of last time already. There's a PV wave limit that corresponds to small p and sufficiently large h so that this thing is non-trivial. In which case you get like a square root of 1 plus some number times p squared. So in that limit, it looks like a relativistic dispersion relation, and that's matched down with the Green-Schwarz string Lycombe gauge. The other limit is giant Magnum. Giant Magnum. This is the limit when you send take p to be finite and large h. In this limit, you forget about y in the square root. You just get 4h absolute value of sine p over 2. And this, after careful classical analysis, you'll find that it matches with this picture of just follow from them, go to action. This actually is not a trivial calculation. I have a section in the notes about it that summarizes this calculation. Of course, it was famously worked out by Hoffman Maldacena. It requires some careful analysis to identify the parameters, map parameters from the classical string description to this Magnum description. In particular, you need to map out what's the relation between the coordinate on the chain and the coordinate in the number action, which is some arbitrary gauge to begin with. So that's the thing you have to be careful about. But it's not a trivial analysis, but just classical physics. And of course, if you're a Hoffman Maldacena, you can use just number action to write groundbreaking papers. Okay, so you know, as you see, you know, this has very non-trivial content already, and it tells you that we know that this h lambda from the one loop calculation is going to be some number like square lambda over 4 pi. I think in my convention. So a prime would be this plus some high order corrections. It was known in the early days that these currents are absent at 2 loop and 3 loop and so on and so forth. And in fact, it is by now known that this is exact in a suitable scheme. That a priori is a scheme dependent you know, statement, right? Because you can always have some scheme dependent finite realization of your tooth coupling at you know, 20th loop order. Who knows? But this turned out to agree with the whatever scheme that one used to do supersymmetry localization calculation. So that turned out to be the canonical kind of answer to this. But from the point of view of integrability, this is going to be literally the only place where the tooth coupling enters. You know, the dependence on Yang-Mills coupling is only through this relation and nothing more. In fact, from the point of view of integrability, we'll never, yeah, I think it's, yeah, we'll basically never need the Yang-Mills Lagrangian again. We're just gonna run with this. Any question before we, well, yes.
Should I think of like the psi and the q bar to be anti-commuting? Like, do I pick up some minus signs if I act? Let's say I have like psi cross psi as you wrote it, and I want to act q bar on the side bar.
Yes, in the usual way. So you know, you can easily keep track of this, of course, by multiplying q with the epsilon for some formal Grassmann parameter. Yes.
Should I think of this like central extension as an anomaly in similar way to like, you know, like the Kyle anomaly where you have some infinite number of fermions and you pick up something from?
No. That has nothing to do with that. Look, No, this is because you're working with gauge invariant operators. So if you set P to 0, this thing goes away. P is the total momentum,
Okay, yeah.
as I mentioned. So it doesn't, it's not in conflict with anything you already know. But of course, you may not have guessed that such an algebra makes sense for the open chain. That's trivial. Yeah, it would be quite hard to recognize the structure if you don't think about the open chain, right? I mean, in principle, of course, because you have to look at the asymptotic regime where the magnets are far separated in order to see this. Now, but on the other hand, I should say that because of some integrated magic, essentially all this beta and stuff are going to be applied also to the situation when magnets are dense, and I don't know why. Right? So that's a big conceptual leap. But that's how integrability works, and they're going to. This is just going to be one of the several assumptions that would allow you to move forward. And I would say up to now, a lot of these assumptions are not justified by first principle, but they are justified by miraculous tests against direct loop calculations. All right, so now let's come to something that's even more important than this dispersion relation, which is the Magnon S matrix. Of course, it's based on this dispersion relation, but the dispersion relation by itself doesn't value that much. Wait, where did the oh, that's good. Here. Let us now discuss the S matrix. So we're going to now assume integrability in the sense of the factorized S matrix in the asymptotic regime. So if you have a situation where the magnons are far separated and they come together, they scatter. The asymptotic wave function is characterized by this S matrix. Integrability would mean the S matrix is factorized, so it will suffice to look at the two-body S matrix. I should mention subtlety before I can continue, which is that there's a kind of a technical subtlety that will play a role at some point. It has to do with the fact that when you scatter these things, in a sense, the length of the spin chain can change, right? Because and there's the kind of this sort of scattering process of the magnet. The classical dimension is fixed, but this phi can turn into psi, and the psi can turn into phi. So which may require to insert a z or remove it. So if you later count the number of fields, the length of the chain would change. That can be handled if you're very careful about how you define the scattering, the asymptotic states. But it does imply that, in fact, the S matrix we're about to describe, at least in the natural basis we use in terms of these spin chain states, will not, strictly speaking, obey the Yang-Baxter equation in standard form, but obey what's known as a kind of a twisted form of the Yang-Baxter equation. This subtlety was, as far as I know, only pointed out in 2006, 2007 by Archinov and Frolov. And they're going to define a slightly different basis, which they call the string theory basis versus spin chain basis. It's a very related by a very trivial way. We'll come to this when it's needed. It just introduced some extra phases to that matrix so that they obey the standard Yang-Baxter equation. That change of basis is something that looks very trivial from the spin chain standpoint, but it will be crucial for the mirror theory, for the mirror model when we discuss the mirror TPA. So, there's some crucial subtlety that if not taken into account, this mirror TPA will not work. But thankfully, Arsenov and Frolov are these, very accurate people, and they're able to pin down that subtlety. But that's story that comes later after that's development after 2007.
I have a question on speaking.
Yeah.
So from this manipulation, it seems that this is a purely a consequence for the algebra, but we are not assuming any properties for the representation.
No, we are assuming that. We're assuming that this thing closes in this way. I mean, I could, Q icons, I could have given some other thing that's not included in my basis, but there are no such thing.
Okay. Ah, I get it.
Right? That's very non-trivial. And of course, it's also very non-trivial that we have the S. You have to assume that there's really a super coherent symmetry. That the S is a super coherent algebra.
Yes, but I think it seems like all of these things are taken care of by the fact that like delta 0 minus H3 is conserved.
Yes, but I'm saying that the existence of super coherent algebra itself is it's a all order, statement with respect to the interaction. It's not it's not a trivial thing.
I'm just a bit curious, like usually for the BPS bound, we see like it only works for BPS multiplets.
This is a BPS multiple. If you have a single magnet, it's a BPS multiple precisely because the representation gets shortened. This is what I mean by shortened, right? This is the shortening condition you see because Q acting on psi is a level 2. This is 2 Q's acting on phi. They could have given you something else.
Oh, I see.
The fact that this is phi itself, that's a shortening condition. This shortening condition would already fail if you consider 2 magna. So it will turn out that 2. Okay, so here's something. Let me just say this. In fact, I'm going to come to this now. If I have 2 magnons, and with momentum P1 and momentum P2, right? So the representation is just a tensor product of these two representations. You can ask, what is that representation? So obviously this would violate BPS bound because there's a violent BPS bound, right? So this will be now in the long multiplet. It's not no longer short multiplet. However, by some miracle, this long multiplet, you can just see that by counting dimension, is irreducible. So it's an irreducible representation of the algebra. Now that's important because if it's irreducible, it means that all the components of the 2 to 2 S matrix elements are related to one another by symmetry. There's only one single overall phase. If you had 3 irreducible representations, you have 3 different phases that cannot be fixed by this symmetry. But because in the irreducible representation, there's only one unknown phase in front. Everything else will be fixed by symmetry. So that's a big simplification. Now it's a kind of a hard, well, not hard, but somewhat tedious calculation to figure out what the symmetry constraints on S matrix are, but these are very nicely established in the 2005 paper of Beisert. That's one of the central results in this 2005 paper, but this is an incredible paper, right? If you look at the paper, this is the sort of the first half of the paper, he worked out this S matrix, but then the second half, which will come to maybe like 2 lectures from now. But for now, we're just going to use the result from the first half of this paper, which is about the S matrix. So the S matrix, so I can be written the following way. Let me write this S matrix, a 2-body S matrix as the S left tensor with X right. So they're going to act on this var phi and var phi bar components separately. Otherwise, all the equation will get 4 times as long, and it's too much, right? So we're going to treat the left and right sector separately in writing this formula. But it'll be easy to put them together once you try to write the beta ansatz. Okay. Let me just write this down first for commenting on other subtleties. Okay, so I'm gonna so you can take this and act on the 2 particle, let's say, in state. You will get some linear combination of. Okay, so here I'm using the following notation. So these indices 1 and 2, which just stands for momentum P1 and P2. I'm not going to keep writing the P1 and P2. And when they kind of scatter, they think of this as them crossing each other, phi 2, phi 1. And there are different ways you can arrange the indices. So let me say there's a term with AB symmetrized. There's a term with AB anti-symmetrized. And then it's also possible to get psi to 1, z minus. With indices alpha, beta. Now they have to, you can handle with the symmetries. So here you've got to have epsilon alpha beta contracted, and you also need the epsilon AB. Okay. Let me just put factor 1/2, like I mentioned. Then there's some coefficients. I'll call this A12 plus B12, and this coefficient is plus C12. All right, so you know, if you only had one species particle, this will just be this SP1, P2 I wrote earlier. Okay, but now you have this bigger set of matrix elements. That's if you if you consider scattering of this phi1a with phi2b. I mean, here I use a notation where I think of S matrix as a mutually operating explicitly on the basis of asymptotic states. If you use an in and out notation, you can just say that this in state equal to this combination of out states. And then you have S psi. Okay, so I'm not going to write down the indices now carefully. I'm just going to say that this equals to some D12 psi with the symmetrized. Still have to. I think I still have to write this. But E12 psi alpha psi beta commutator so that is 1, 2 to 1 to 1 and plus 1/2 F12 epsilon AB epsilon alpha beta phi A2 phi B1 Z plus circuit. So I've got that. I've got two more. There's the psi phi and phi psi. Okay, so you can look up the formula. I'm not going to keep writing this, but they involve 4 more things. G12, H12, K12, L12. So you got total in these 10 S matrix elements that are constrained by this using just the bosonic symmetry. But now, if you use a centrally extended SU2/2 symmetry, you'll find that they're all fixed with one another up to overall phase. Just to now, this is somewhat non-trivial. This you really have to calculate, and there's no easy way around this. The actual formula is also pretty long, but is absolutely essential. And if you want to get familiar with this, you have to kind of play with this formula yourself. But in fact, before I describe what the result even look like, I mean, first of all, I have to write down all the 10 coefficients. Let me not try to do that on the board. Even in order to actually write the answer, I need to introduce actual notation, because if you try to express that in terms of the momentum P, it'll just look some horrible mess with many square roots and so forth. Okay, so at this point, I'm going to introduce some way to parameterize the momentum P in terms of a nicer spectral parameter. This parameterization is also going to allow us to work with understand the analyticity property of the S matrix better. So let me define the following quantities. I just erased A, B, C, D, but I'm gonna use them. We're gonna define X plus to be I times VP over BP, and X minus defined to be minus I AP CP. Now you don't have to remember this definition. You just need to know that this X plus and X minus is some function of P that will be fixed. But here's how we'll actually use them. So you can show by checking this ABCDE relations earlier that they're related to P in the following way. So X plus over X minus is e to the IP. So the ratio between the two is e to the I times the momentum. And then they obey the property that X plus 1 over X plus minus X minus minus 1 over x minus is equal to I over h. This is somewhat unfamiliar formula if you've never encountered the subject before, but it's going to come up all the time from this point on. And at some point, you'll know this by heart, even though right now this looks like a very strange expression. All right. So we have these two relations. So of course you can solve, you can plug in the mathematics and solve x plus x minus in term p. You get something like formula with square roots, not very illuminating. All right. But those square roots are going to be crucial because the analytic property of that measuring with vector momentum will play a crucial role because we're going to discuss later crossing relation, which require analytic continuation. Every paper you're going to see on the subject of the spin chain, S matrix, and beta ansatz, you're going to see this x plus x minus all over the place. Right? So this is the definition. I should say that in the literature, people use different normalization conventions. Sometimes people rescale x by a factor of h. So my convention may differ from some papers by some factor of h, just the normalization convention. Also, people often write g instead of h with little g, and the g is written by h by square root 2. So there are all these conventions, but I try to make sure the conventions within the notes are self-consistent. I think like often you'll find that Archinov and Frolov use a convention different from Beiser by a factor of square root 2 and so forth. That's easy to translate. So whenever you look at paper on this, you have to make sure you know the convention for the x plus and x minus. Now, that is right. The dispersion relation for the magnon. The energy is can be written in the following way. There are two equivalent ways to write this. You can write the energy to be minus 1 minus 2 IH x plus minus x minus, or equivalently plus 1 plus 2 IH of 1 over x plus minus 1 over x minus. These two are equivalent. This looks very strange, but this will also play an important role later. So just to give you a flavor of this, so for example, just to get some kind of very rough intuition. In fact, maybe let me okay, so let me for now just say that if in the small h regime and the real momentum p, we can take x plus minus to be e to the plus minus ip over 2 over 2h sine p over 2 plus I over the. Okay, so anyway, this just easy to check. Yeah, that's kind of obvious. So plug into this, you get the correct expression relation expanded to the unit trigger quadrant. Actually, yeah, we got h squared. That's correct. That being said, let me now discuss a interesting observation based on this formula that so far may not affect me very much. Of course, remember we have originally had this formula in squared. All of these are equivalent. Now there's a square root here, and so if you want to continue in the complex momentum plane, which we're gonna do, soon, maybe not today. You can go around the branch cut of the square root. Now that's going to be important for crossing symmetry, because the crossing requires a configuration where you send EP to minus E minus by any continuation. And so, when we discuss crossing, well, that's that was needs to be done. And looking at here, and the end here, you can see that this can be accomplished simply by sending x plus minus to 1 over x plus minus. So that will do the crossing. Now, what all this estimation element you're gonna write down are going to have some analytic property with x plus and x minus. Okay, first of all, you have to be a little careful with this kind of manipulations because this transformation preserves that constraint. X plus and x minus are not independent variables. And that's something I have to get used to. It's a bit requires some brain gymnastics because they're not independent variables. They're tied by this relation. The thing is, we do not want to solve this relation necessarily explicitly because it cannot involve square roots. And this identity property is kind of important to keep track of. Later on, we'll see that if there's some kind of very non-trivial infinite Riemann sheet structure of the S matrix over the complex B plane. So there's a branch cut, go over a branch cut, discover infinite many branch cuts, and go over the branch cut, discover infinite many more branch cuts. A complicated structure. And so you don't want to solve the relation. You want to keep this relation. You have to. So you can when you discuss an integration with that x plus or x minus or p. So it's not like you can allocate to x plus and x minus independently. For example, so you cannot flip them independently, but you can imagine some integration such that eventually you go from taking x plus and minus and you invert them both. In which case, this will be satisfied. If you do that, though, you see that you are necessarily going to go outside of the perturbed regime because perturbed regime, the x plus minus needs to have large modulus. They're large numbers, but then you have to go to small x plus x minus. So this already tells you that this crossing relation, if it makes any sense at all, of course, it will be true. Otherwise, I will not be telling you. I mean, that's true in the sense that it passes through many checks and everyone believes it's true. This crossing relation is necessarily non-perturbative. So that's something very important to recognize. It's going to tie the strong coupling to weak coupling in a way. Okay, so that's already very non-trivial. The crossing relation can be understood purely within the strong coupling region, but it cannot be understood purely within weak coupling. In some sense, that's may not come as a surprise, because why should there be crossing in the first place? The usual reasoning is that it's because it exists in the string worldsheets. There's a relativistic theory on the worldsheets. That's kind of the heuristics. It's totally not clear why, from the spin chain perspective, why you should have such a thing as crossing, because it's not a discrete system. Why should you be allowed to continue the momentum? And it's like because there's usually we think of this anisotropy as related to microcausality, like locality. Of course, on spin chain you don't have microcausality, so what the heck are you talking about? So at least conceptually, this kind of it's not even conceptual, it's more like philosophical level. Right? At this philosophical level, we think of the crossing is having to do with string worldsheets. Okay, so in terms of so I think I'll just this will be just the final point today. I will write down what the result kind of looks like. I'm not going to write down all the 10 formula, but write down a few that are simplest just to illustrate the kind of relation you get. So it turns out that if you solve this constraint, you find that the A12 is S12 times x2 plus minus x1 minus over x2 minus x1 plus. And B12 Oh, it's already kind of long, but I'll just write down this and no more, x2 plus minus x1 minus over x2 minus 1 plus, 1 minus 2, x2 plus minus x1 plus over x2 plus minus x1 minus times, x2 plus, sorry, x2 minus over 1 minus 1 plus, x2 minus times 1 over x1 minus, and so forth. Okay, so we have, you see, these formulas are already pretty complicated. And if you try to write this in terms of square roots, then well, in one term you will be completely unrecognizable. All right, so that's it's really non-trivial, but all of that just follow from the symmetry. But let me come to the upshot here, which is so let me just make a statement. We'll discuss its justification later. We then rewrite this S12 as the following. Okay, so first of all, remember that we have the left and right sector. We have to tensor them together. So I'm just doing one sector for now. S12 is going to be equal to this is just a definition, something times sigma 12. So something is x1 minus x1 plus x2 plus minus there's a kind of a redefinition that expresses this in terms of some sigma 12. This thing is called the dressing factor. Okay. So I think up until 2005, it was thought that the dressing factor was 1, and the problem was solved because they were able to compare the beta ansatz, the prediction of the beta ansatz to calculations up to explicit calculation up to 3 loop order, and it agrees perfect. All right, but then I forgot what the order of how the order of this goes. Whether it was known that there's a disagreement at 4 loop order. So this is a result of a lot of hard calculations. So it was known that if you set the dressing factor 1, agrees up to 3 loop order, but disagrees at 4 loop order. That was before the crossing symmetry was a thing. Yeah, the subject developed very quickly around 2005 and 2006 because the Binder paper is like, I think it's like 05, 11, and the crossing symmetry was understood. I think it was 06, 03, the Bionic. So we'll discuss the crossing symmetry will be the central subject next time after the break. It's going to constrain the dressing factor in a non-trivial way. We'll see that if you set the dressing factor to 1, it's actually inconsistent with crossing. So the sigma 12 is going to obey some crossing relation that says sort of sigma 12, sigma 1 bar 2 is equal to something non-trivial. And this bar, roughly speaking, means turning particle into antiparticle. We'll have to explain exactly what that means. Sorry, I mean the bar. Okay, well, not quite. The bar here basically means this continuation. All right, but you have to define that with a suitable continuation. So even the definition of this is non-trivial, but the crossing symmetry will imply that sigma 12 times sigma 1 bar 2, where sigma 1 bar 2 is defined by the continuation, is going to be equal to some expression in terms of x plus and x minus, x1 plus minus, and x2 plus minus, which is non-trivial. Things like this kind of format. It's impossible to remember. And it's very non-trivial to find a function that satisfies that crossing relation. By trying to solve that relation alone, will produce the orderly expansion. Why orderly expansion? Because H enters everywhere. That's the coupling. As I said before, the only place where the Yang-Mills coupling or the tooth coupling will enter is through this H, middle H, everywhere. And so every time you write the expression of x plus and x minus, the H is always implicit because it comes in this relation. So even though you don't see the H explicitly here, it's really there, right? And when you solve this, you'll find some horrible function that will solve the crossing relation. Now give an order expansion. So of course, you have to make some guess in order to find the solution. It's kind of the minimal solution that satisfies this. And already just level of looking at the solution crossing, it passes extremely natural check, which is at for loop order, there's a coefficient involving zeta3 with some coefficient that matches on the nose. So it's something spectacular. So we'll discuss that next time. In fact, this formula for the sigma 1, 2, when they first guessed it by there was a kind of two papers, one by Pfizer, Hernandez, and Lopez, the second one by Pfizer, Eden, and Stadecker. They guessed the expression, but it was in the form of some series expansion, just total mess. I think it was a year later, there was a paper by Duray, Hoffman, and Maldacena, where they found the integral representation. It turns out the log of this is a double integral of some ratio of some like log of gamma functions. Okay, so it turns out that there is a nice way to write it. Well, nice, relatively speaking, it's like double integral of a log of gamma. Okay, something. So anyway, that's kind of the one of the most spectacular results in this part of the story. So the part one of integrability is going to be the climax of that story is going to be the exact answer of the sigma 1, 2, the dressing factor. And then once you have that, you can plug that into the beta ansatz for the SL2 sector, which involves this inserting this D plus into spin chain. And in the limit, when the D plus is very dense and a very large number of them, that will allow you to calculate the spectrum of this long spinning string and read out the Caspar on dimension. So that's the logic. But I think we have gone for long enough. Yeah.
So how do people come up with this parameterization for the x plus x minus? Like, how did they guess?
Let's see. There's something similar already. There's some similar parameterization already in the case of the Heisenberg spin chain, which I did not discuss. But this is kind of some kind of deformed version of it. I'm not actually sure of the history of exactly how this was. How people exactly come up with this, but the thing is, if you play with this formula long enough, you kind of find that this is kind of unavoidable. Basically, I don't have a very, the thing is, you basically need to undo the square root. You kind of look like it's basically hard to find some parameterization that undo the square roots and the sign. So you kind of want to express it to IP in something and get rid of square roots, and this is basically okay. You're gonna end up with this. Yeah.
I think you already mentioned it about the changing of the length of the chain.
Yeah.
But in terms of how to know when the Z minus and the Z pluses appear on the right-hand side here, should I think of that like from I want the S matrix to commute with the Q and the S, and the Q and the S will add Z pluses and Z minuses, or like how should I think of the Z minus?
Well, it's literally still Q commutes with the S matrix, of course.
Okay.
I mean, it is just that, right? Because Q act on this will sometimes insert Z plus or Z minus, right? It's just that. It's just that. There's a way to, as I mentioned, there's a different kind of asymptotic basis you can define that differ from this by some phase, where you remove the need for inserting this Z plus and Z minus explicitly. It roughly speaking corresponds to it's like saying that I work in the basis where I replace phi with phi multiplying Z plus to a half. So you can formally define such a basis. It actually makes sense. And with that basis, you kind of don't have to worry about this. Yeah.
So in principle, there could have been more terms, but then those would always get killed by acting with either Q or S on both sides.
Sorry, what more terms are you referring to?
Like, let's say side 2, side 1 without a Z minus. I just know that can't be there because if I act.
Oh, no, but then you need to know that. I mean, now you can, just by looking at the classical scaling dimension.
Oh, okay. I
Yes.
see.
Yeah, that you don't have to. That's clear.
Right, because the size are pretty house.
Yeah. Yeah. Um, Yeah, I should say that, in fact, it's not totally obvious that this thing that's the base fixed by the symmetry of the dressing face satisfies Yang-Bax equation or the twisted version of Yang-Bax. You would like to check that. It's not entirely guaranteed. In fact, this is not trivial to check. This you have to write a computer program because like nobody wants to check this by hand. I think in the Weidner paper it was mentioned that I forgot whether when the paper was written this was checked or not, but I think there's some comment about checking this. In fact, because this if you read the homological paper on like the OM model, the Yang-Bax equation plays a non-trivial role in constraining the OM symmetric S matrix. Here, yeah, right. So, yeah, this. So here the statement is that. Okay, I think I think the point is basically this. You see, in the OM model, you had the particles in the fundamental representation of OM. And when you take the tensor product, you're in a reducible representation. So there are several independent coefficients up to the OM symmetry, but they're further constrained by Yang-Bax equation. I think that's the story there. Here, the Yang-Bax equation will never constrain the overall phase because the overall phase is always the same when you one way or the other. But here, the point is that there is no other independent coefficients. And it just happens that this also satisfies Yang-Bax equation. I mean, I don't know if there's some general reason I can tell you that it guarantees to satisfy Yang-Bax equation. Of course, if it didn't, the whole thing will fall apart. But it works. I mean, the later paper of Arjunov and Frolov, they wrote this other basis. So it's very long formula you can look at and they checked the Yang-Bax equation. It's a huge mess.
So far the assumption has been that like the SU2/2 twice like holds at the quantum level. Is that the assumption? And the
Yes.
That seems like a pretty minimal assumption, right? Or like
but this is only a small part of the assumption though. The crossing symmetry is the next big assumption. That one I would say is much more substantial than this and requires more of a conceptual leap. So as I mentioned, there are several assumptions. There are, I would say that they are there are four crucial assumptions in the step along the way. Integrability, of course, this factorization of S matrix. There's going to be the crossing, which will be different interest factors. That's a huge assumption, and that I would say is the most non-trivial thing because even the form of the crossing itself takes some thinking to figure out. It's not something totally trivial. Then there is this asymptotic beta ansatz, which basically says that this beta ansatz also works for the chain when you're very long, but you allow the magnons to be dense. That's another big assumption. It's not obvious. Just think about scattering problem. It's not obvious why that should be true. And then there's mirror TBA, which will come later. That's so four big assumptions.
But is factorization even assumption here? I thought you said they checked it like on the computer, like
No. That's no. The check is that factorization is consistent with integrability. I'm talking about the integrability itself. Why should the three-body S matrix factorize into product of two-body S matrices? That of course will easily break if you change the Hamiltonian by a little bit. If you add some arbitrary to next to nearest neighbor interaction, you will easily violate integrability. Like generic spin chain, Heisenberg spin chain, you have XX one half model. You might say that, oh, if I have a SO3 rotation invariance on the spin chain, at the one loop level, it's automatically integrable, yes, but you can check that at two loop level, it's not. So if you had written this H2, it's gonna involve like PL L plus 1 and also PL L plus 2, right? You can have such things, you can exchange the next neighbor. There's a relative coefficient. Only for specific linear combination, it's integrable, otherwise it's just not. So this is very non-trivial. It's not by no means guaranteed. If you only think about the speed chain. It's really some miracle, just even for this factorization to hold. I mean, there was some suspicion. You can ask, what's the thing that gave rise to this factorization property? Is it just large n or is it square symmetry? I think this is not really clear. At the time, there's a paper by Witten that tries to understand whether this integrability could exist in pure Yamu's theory, large n. I think it was not conclusive. I don't remember exactly what conclusion was drawn, but my impression was that it was not conclusive.
Like, dress better or
Sorry, say again?
Rossen?
Yeah.
Will only come into play when determining the dress better or to get the A12, B12.
Well, I mean, all of these are tied to each other, right? So the crossing, for one, fix everything. So the thing is, what is crossing? The crossing is the statement that, very roughly speaking, 1, 2, 1, 2 is equal to the turn is 90 degrees. So let's say 2, 1 bar, 1 bar, 2, something like this. Okay, that's pictorially what crossing is. The non-trivial thing is to understand what does this bar mean. In the Yannick paper, they call this the antipode of the Hopf algebra. So it has some way to determine this by thinking about the Hopf algebra. I don't really understand this approach. I never really studied that algebraic approach in detail. But it turns out that you can understand this crossing very easily by looking at a specific component of this, which turns out in this label will be G and L, which I didn't actually define. But it turns out that the crossing is mostly easily realized on G and L, and it's a little bit more complicated if you're trying to express in terms of A, B, C, D. So, but it's worked out in full detail by this Yannick paper. The Yannick paper is actually kind of amazing because somehow it does all this analysis of the Hopf algebra, which I don't really understand. I never tried to understand it. But he kind of solved everything just by thinking about this underlying algebraic structure. Yeah, so for example, this is not going to apply easily to just like A12 by itself, because you have to ask what is the correct notion of antiparticle of phi1? Is it phi2? Is it something else? Does it come with a coefficient? Maybe it comes with some phase? It's actually not obvious. It's right because this is not a relativistic system, so it's kind of non-trivial to understand what it means to take particles as antiparticles.
Just to be clear, once you've written this down and applied that the S matrix should commute with Q and S, you get all the A, B's up to L in terms of some single fixed parameter.
Correct.
S. And then once you have the dispersion, you can write it even further. I guess, or maybe this is just a way to rewrite it in some simple way, but then it's only with crossing that you can solve from what the sigma is supposed to be.
Yeah. I mean, up to now, the sigma is an arbitrary function that I don't know, right? It's some arbitrary function of momentum or in terms of x plus x minus. So it's a function of x1 plus minus and x2 plus minus. We just don't know what it is up to this point. You can choose any sigma that's satisfied the Yang-Mills equation, and of course, it's supposed to also satisfy unitarity. But that's easy to verify. So for example, you can verify that when sigma of 1 is set to 1, this is actually unitary. Like if you want to actually want to work with the same expressions, you have to have this stored in your Mathematica. So I have actually checked that it's unitary, even though I didn't actually derive all the individual coefficients.
So from the string field theory point of view, like the main obstacle is like finding out what the magnon is, because we can assume the algebra and all these things, but we don't know what the what the phi and like psi is and so on.
So as we discussed earlier, this magnum, you know, while it's the most natural thing from a spin chain point of view, it may not be the easiest thing from the string field theory point of view, because you need to consider some incantation on the string that have a very large momentum quantum number on the finite size circle. Because here we're taking sort of very long, but if you scale to the one size circle, you need to consider also the modes of very high momentum and localized. So it's not so easy to recognize the structure of this locality if you just write operators like e to the ikx partial n x, and you kind of have to Fourier transform it back to this n, right? I don't know. And okay, so you can have the Fourier transform. So that sounds pretty horrible, right? Maybe it can be done. Maybe it can be done, but it's not necessarily the best strategy, because you know the string field theory is such a different description of the system that you know things that are hard in one might be easy in the other, and vice versa. So, as I was suggesting earlier, this TBA mirror TBA equation, the Y system, which is going to be the the end of the what the integral story is going to lead to, which has a very complicated chain of logic. Might actually be more accessible from string field theory than the individual magnets. But of course it's you don't know until you try. But I'm just saying that you should not. It's just because the magnet is the easiest thing in the integrability approach, it doesn't necessarily mean that's the first thing to look for from the string field theory perspective. In fact, in a sense, because thanks to all this integrability work, we understand how tightly things are constrained by the symmetries. We do not have to repeat that work from string field theory. It's not like we're trying to translate everything to string field theory. There's no point in doing that. We just need to establish the underlying principle from string field, like the existence of the symmetries. We don't have to necessarily identify what the magnon state is if we actually know what the symmetry is. Because a lot of this will just follow, right? You see, all of this just follow from SC2 centrally extended. Now, you have to know that KP, of course, that part is not trivial, right? So when I say the centrally extended, you have to know how the central charge gets mapped to the momentum. But on the other hand, who says you have to parameterize with the momentum? You can parameterize anything you want because you can change to some other special parameter. You just want to know the actual energy at the end of the day, this Hamiltonian, which enters the algebra. You don't actually need to know which one you call the magnet momentum. In fact, the momentum itself is a gauge-dependent thing. If you change the coordinate on the worksheet, you change what you mean by the momentum. That's actually what happens in the giant magnon story. In the giant magnon story, if you work in the conformal gauge, Nambu-Goto, that worksheet coordinate isn't the spin chain coordinates. In fact, in Hoffman and Molesina, they have to do some extra work to figure out what the map is. I mean, it's not hard to figure out because they just need to look at the angular momentum density, because the spin chain is such that it has constant angular momentum density. Because the number is like the z, the counting number of z's. So if you calculate using Nambu-Goto to calculate angular momentum density, you'll find that you map to a new coordinate system where you have the constant angular momentum density, and that coordinate system corresponds to the spin chain.
Like related to modular invariance.
Yes. I mean, the mirror TBA is just double Wick rotation. It is. We are just swapping space with Euclidean time. Now, once again, what does that mean for the spin chain, right? Because it's a discrete system, there's no, you can't literally swap space with time. And in fact, the precise statement isn't that you're swapping space with time, but you're swapping the space and time of this spin chain system with the so-called the mirror model, the mirror theory. What is the mirror theory? It can only be described in the integrability language, which is that you can talk about the mirror magnons and their S matrix. So their S matrix is literally the same as the S matrix of the magnon. It's just that you view this x plus and x minus as, here you write this function p, but the p becomes I times the energy of the mirror magnon. So the dispersion relation gets swapped. The p and e gets, so the relation is going to be something like this. It's going to be p equals I e tilde and e equals I p tilde, where the tilde variables are the energy moments of the mirror magnet. Now this sounds totally crazy, but it turns out that even without doing any work, if you just take a dispersion relation, there's some it produces some feature of perturbation theory that's highly non-obvious. We'll discuss this later. I mean, it's going to take too long right now, but all these guesses on the face of it sounds completely crazy, but historically, it wasn't that how people just make this guess to begin with. There was a non-trivial check because at the beginning people weren't so ambitious as to, let's just solve the Konishi. That seems to be too difficult. But people wanted to say, let's first calculate the first order wrapping effects. Because if you say that the asymptotic beta envelope doesn't capture the finite chain, that itself is non-trivial because you have to actually test against some data, from perturbation theory calculation to know whether it works or not work. But it was known it doesn't work. At the beginning, people just want to calculate the first order wrapping effect. You have some exponentially suppressed correction. You just want to calculate what the first order correction is. And it turns out that by thinking about this mirror TBA, you get the first order correction correct. This was done by Yannick. So they get a very natural match of 4 loop order by some miracle. And then people, of course, believe that now this actually makes sense. And then Archinov and Frolov just ran with it and found the whole thing.
So to get this screwed, like we didn't really need to know the representation of the fields, right? We could have just known like what the algebra is and then look for like the BPS bound and so on.
That's correct. That's correct. So in fact, later, starting from 2007, Archinov and Frolov tried to derive all of this from the Green-Schwarz and Lycombe gauge. So, obviously they don't have these fields, this phi and size, but they have the algebra. They can recognize the algebra from the Green-Schwarz formula. And they basically arrive at the more or less the same conclusion from that. It's a little hard when you read the paper, whether they took any assumption from the speech chain story or not, but I think not really, right? But the thing is, it's not totally obvious because by that point they already know all the results from the spin chain. So it's like, okay, they know what they're getting. If you didn't know any of this, can you really, find everything from the Green-Schwarz? I think you can, but it's not, totally obvious if you look at the papers.
And so they like express the charges in the Green-Schwarz fields, but like they just like use the algebra to get the BPS bound. So
yeah, but they recognize the algebra explicitly in the Green-Schwarz fields, I think. But that's like in the part of the paper that nobody reads, right? Like once you derive this, you can you just use the results. You don't actually need to know. But yeah, that's what the one with Archinov, Frolov, and the 2 other authors, Plevka and one other person. So I think it was 2006, 2007. In fact, I think at the time, okay, I don't exactly know the history of development on this at the time, but I'm pretty sure that like the spin chain folks didn't care about it until the mirror TBA was really kind of emerged out of that picture. Because at the beginning it seems like you just by thinking about Green-Schwarz or just reproducing the same thing. So what's the big deal? But you kind of need that thing to be able to understand mirror TBA precisely. Like the mirror TBA is not something that is easy to guess just by thinking about the speed chain picture. So I would say that's a place where you really need some intuition from the string theory side. Otherwise, this thing looks totally crazy.
So if just the algebra is used, one could just assume it exists in the string field theta, and then it's sort of like a trivial exercise just to find a BPS bound, I guess.
Oh,
but
well,
that-
I mean,
that's not-
this, you need to know how it acts and acts on what, right? That's going to be the key. I mean, I haven't described the TP and Y system. So I mean, it's not there, there's some very specific quantities, these pseudo energies, the mirror magnons. I don't know what they mean in the string field theory description. So the symmetry has got to be there, because the symmetry are all inherited from PSD comes to /4. Well, of course it's there. The symmetry of the ADS5 times S5 background. But the symmetry act on the individual magnons in some way, and it's the natural thing is to recognize what the symmetry acts on and how it acts.
And that was done in the Green-Schwarz.
Sorry?
Somehow in the Green-Schwarz, they know on what it acts.
Yeah, because in the Green-Schwarz, yeah, that's right. That's right, because sometimes in the Green-Schwarz, you can identify the magnon excitations, right? I mean, the Lycon gauge, because, they literally are the oscillator excitations. So if you're in Lycon gauge, you can go to, the thing is, in Lycon gauge, you naturally have this open chain description, because in the Lycon gauge, the length of the string is the Lycon momentum, which is like the J. So you naturally can just go to the infinite chain. That's sort of one of the advantages there.
So there's some version of this K plus and minus in the Green-Schwarz description as something acting on the string worksheet.
That's gotta be true, but that's actually a part of the Arjuna Frolov work I've never studied. So I actually don't know the derivation. But let me think. Do they even need to, let me see. Do they really need to know? Okay, so you see that's the thing. Do they need to know what P is? Because I'm not sure that they do. Right? You see, if I didn't express my KP in certain P, just call it K. I just assume that exists. I think everything is just as good because I still have X plus X minus. This is just replaced by like some expression 1K. But I can still do everything I need. Okay, so no, but that's not quite true because I need to know this because this is going to go into the beta ansatz. Yeah, so they've got to know P. Let me see, because the e to the IPL is going to enter this. That's where you really need the momentum. Just knowing the K is not enough. Yeah, let me see. Who do they? Yeah, that actually seems not trivial. In fact, I don't remember how they.
Would that P be like Fourier transform with respect to those kind of ends as you go before? Or?
Well, I mean, it's no, I mean the P is and, right? I mean, and
Oh, okay, yeah.
yeah, it is just that. But yeah, see. Derivatives and charts. Yeah, apparently they have derived it. How did this actually work? Well, apparently there's an untrue calculation. They ran some charges, some supercharge on the in the worksheet theory in the Lycan gauge, and actually derived this this e to the IP minus one or one minus e to the minus IP expression. It's there. It's like the first reference I posted in the integrability channel.
They also have this like 150-page review on this ABS5 string. Is that like so good?
Which year was this?
2009?
What's the number?
Uh,
I put that.
0901.4937.
So this is all about the Green-Schwarz approach.
They derive the central charges on like page 93 or something, I guess. That is.
Yeah, I think it's the same as in their papers. Yeah, I mean, it seems to like nice review. Of course, this it sort of ends at the crossing. Ends at the crossing.
Or you can just go like foundations of ABS5 superstring very fast.
Yeah, I mean, it's not really different from their papers. Yeah, I think in this review they basically kind of get to the crossing with just the logic of quantity in Green-Schwarz action. So indeed, because we say that from the equal-Schwarz Family, the only input was the algebra of the magnetic differential relation. If you can derive that from the Green-Schwarz, that's just equally as good. Everything else is assumption. Of course, in the theory, you can also do further calculations. But
Um,